Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Length of longest Fibonacci subsequence, Leetcode 873. If you are new to the channel, consider subscribing. I try to make daily videos on the problems related to data structures and algorithm, including detailed explanations, optimized solutions, and step-by-step walkthroughs to help you improve your coding skills. Now to the problem. A Fibonacci-like sequence is a sequence where the sequence has at least 3 numbers, and starting from the third number, each number in the sequence is sum of 2 numbers before it. For example, one Fibonacci sequence starting with 1, 2 can be, we have the third number like 1 plus 2 that is 3, 2 plus 3 that is 5, 3 plus 5 that is 8, and so on. And now the problem says, given the strictly increasing array R of positive integers forming a sequence, so strictly increasing means there are no duplicates, we should return the length of the longest Fibonacci-like subsequence of array. If 1 does not exist, return 0. And then they have defined subsequence as well. A subsequence is derived from another sequence R by deleting any number of elements including none or 0 elements from an array without changing the order of the remaining elements. For example, 358 is subsequence of this array because we can remove the elements 4, 6 and 7 and we will get the elements 3, 5 and 8 in the same order as in original sequence. Then in example 1, for the given array, one Fibonacci sequence we can form is starting from 1 and 2. So 1 plus 2 will be 3, then 2 plus 3 will be 5, 5 plus 3 will be 8. So this Fibonacci-like sequence has length 5. Another Fibonacci-like sequence will be that we start from 1 and 3. 1 plus 3 will be 4, 4 plus 3 will be 7. So this Fibonacci-like sequence has length 4. And one more Fibonacci sequence can be that we start from 2 and 4. 2 plus 4 will be 6 and this will be of length 3 and so on. But we have to return the length of the longest Fibonacci sequence. So we will return 5 as our answer. Similarly, in example 2, we try to form the Fibonacci sequence starting with 1 and 3. But the next element, that is 1 plus 3 equal to 4, is not present. Then we try 1 and 7. But 8 is not present. Then we try 1 and 11. And 12 is present. So we can form one Fibonacci sequence between 1, 11 and 12. Another Fibonacci-like sequence will be 3, 11 and 14 or 7, 11 and 18. All of them have length 3. So the length of the longest Fibonacci-like subsequence will be equal to 3. Now in terms of solution, one of the naive approach can be that we use backtracking to generate all possible subsequences of an array. And then for each subsequence, we check whether it satisfies the Fibonacci property. That is, every number in the sequence is sum of 2 preceding elements. And as we do this, we would track the maximum length of a valid Fibonacci-like subsequence found. But the time complexity of this approach will be exponential because for an array of length n, number of subsequences we can generate is 2 to the power of n. And then for each subsequence, we check whether it satisfies the Fibonacci property. Hence, the overall time complexity will be O of n into 2 to the power of n. And now the question is, can we do better? And the answer is yes. We can significantly improve the solution by following the process which we use in the example walkthrough. We know that in the Fibonacci-like sequence, every number is a sum of 2 preceding numbers. Let's denote it by first and second. With this in mind, we can pick up 2 numbers, first and second, as a potential Fibonacci-like subsequence. This can be done by running the nested loops. For every chosen pair, then we can calculate the third or next number as the sum of first and second and check if it exists in the array. If it does, we extend the sequence. If it doesn't, we stop the sequence. For example, first we pick up 1 and 2 and sum them up and get 3. Then we check, is 3 present in the array? The answer is yes. So we extend the sequence and now our first becomes 2 and second becomes 3 and we again sum them up. So we will get 2 plus 3, that is 5, and we check, is 5 present in the array? The answer is yes. So we extend the sequence. Now first becomes 3 and second becomes 5. We again sum them up and get 8 and we check, is 8 present in the array? And the answer is yes. So we extend the sequence and now first becomes 5 and second becomes 8. Again we sum them up and get 13 and check, is 13 present in the array? The answer is no. So we stop the sequence and the length of the sequence was equal to 5. Now Since we are looking up for this third element repeatedly using a linear scan in the array, that takes O of n time. So instead, we can use hash set to optimize it to O of 1. So we can add all of these elements to the hash set and check for the presence of third element in it. So similarly, we will continue with our nested loop, and the next pair we will form is between 1, 3. So first is 1 and second is 3. So we sum them up and get 4 and check is 4 present in the hash set. The answer is yes. So we extend the sequence, and now first is 3 and second is 4. So we sum them up and we will get 3 plus 4, that is 7, and we check is 7 present in the hash set. The answer is yes. So we extend the sequence, and now first is 4, second is 7, and we sum them up, and this time we will get 11, which is not present in the set. So we stop the sequence, and the length of this sequence is 4. And similarly, we will check the length of sequences formed from pairs 1, 4, 1, 5, 1, 6, and so on. Similarly, we will go through all the pairs starting with 2, like 2, 3, which will lead to sequence 2, 3, 5, 8 of length 4, or the pair 2, 4, and so on. So out of all of these sequences, the longest one will be 1, 2, 3, 5, 8 with length 5, and that will be our answer. Here is a quick code walkthrough of the solution we just talked about. We have Java code on left and Python on right. First, we will create a hash set called numSet and store all the elements of array into it. Then we initialize max length to keep track of the longest Fibonacci-like subsequence found. Now we run the nested loop. I represents the index of the first number and j for the second number. So we get the pair first and second from these indices. And because of this, the length of current sequence will be equal to 2. Now let's compute third as sum of first and second, and this should be the next number in the sequence. So we greedily check if the number exists in the set. If it does, then we extend the sequence by setting first to second, second to third, and increase current sequence length. And now calculate the next number in the sequence by adding first and second again, and continue with this process as long as the third element exists in the set. And before we start the same process for the next pair, update the maximum length from this current length. And once we are done with all the pairs, we check if the max length is less than 3. If it is, it means no valid Fibonacci-like subsequence exists, so we will return 0. Otherwise, we will return the maximum length. Now in terms of time complexity, it will be O of n squared log m, where n is the number of elements and m is the maximum element in the array. Because first we are building this set that takes O of n time, but then to iterate over all the pairs in the array, we run the nested loop that takes O of n squared time. And then for each pair, we continue to calculate the third or next element in the innermost loop. But it may look like that it is an O of n operation, but actually it is O of log m operation approximately, because the third element is calculated in the Fibonacci sequence, and Fibonacci sequence grows exponentially. For example, if we see first two elements is 2 and 3, then the next will be 5, then 5 plus 3 will be 8, then 8 plus 5 will be 13. So each number in the sequence is almost doubling. So because of this, the time complexity of the innermost loop is O of log m, and the overall time complexity is O of n squared log m. In terms of space complexity, it will be O of n for storing the numbers in the hash set. Now the greedy approach works for extending the Fibonacci-like sequences, but it does repeated calculations. For example, you would have already noticed when we start the sequence with pair 1, 2, we get the Fibonacci sequences 1, 2, 3, 5, 8. Similarly, when we start the sequence with pair 2, 3, that is first is 2 and second is 3, we get the sequences 2, 3, 5, 8. Or when we start the sequence with pair 3, 5, we get the sequences 3, 5, 8. The length of this sequence is 5, this one is 4, and this one is 3. So as we go from left to right, these sequences get shorter, but they have same overlapping portion. So to avoid these repeated subproblems, we can use dynamic programming, as it works great with these overlapping subproblems. And instead of going from left to right, we can go from right to left. This ensures that the shorter subsequences are solved first and can contribute to solving the longer subsequences efficiently. For example, consider the sequence 3, 5, 8, which has a length 3. We can store its result in the DP matrix for the future use. The indices of the array are 0, 1, 2, 3, 4, 5, 6, 7. So we can create the DP matrix of size 8 into 8, where for every pair ij, we store the length of the sequences starting at these indices. For example, for the sequence 3, 5, 8, it starts with numbers 3 and 5, which are stored at indices 2 and 4 respectively. So dp of 2 and 4 will be equal to 3. And later we calculate the length of the sequence starting with numbers 2 and 3. So we have to calculate dp of 1, 2 because numbers 2 and 3 are stored at indices 1 and 2. So we sum them up and their sum will be equal to 5, which is present in the array. So this means that this sequence can be extended. So we take dp of 2 and 4 and add 1 to it, because this is where the length of the sequences starting with 3 and 5 are stored, and we just add 1 to it because number 2 was added to it. Also, when we add the number 2 to 3, we get value 5, but in the dp array we are storing the indices. So now instead of using a set, we should be using a map to store the numbers to indices mapping, because then for the number, for example in this case 5, we can get index in just O of 1 time. So for number 5, the index will be 4. So we can write the generic recurrence relation as, suppose we have already calculated length of the sequence starting at pair j and k. Then later we have to find the number I such that nums I plus nums j is equal to nums k. Hence dp of ij in this case will be equal to dp of jk plus 1. So now let's quickly see this in action. First we will create the number to index map. So for example, for number 1, the index will be 0. For 2, it will be 1 and so on. Now we will start filling in the dp array from the back and start iteration on the array from behind to form the pairs. So first pair we form is 7 and 8. We sum them up, we get 15, but 15 is not in the index map. So we set the length of dp 6, 7 to 2, because that is the length of the longest sequence that we can form from these numbers. Similarly, we will try 6 and 7, 6 and 8, 5 and 6, 5 and 7, 5 and 8 and so on. For the demo purposes, let's write dp of 5 and 8. So we sum up 5 and 8 and get 13. But 13 is also not in the map. So dp of 4 and 7 will be equal to 2 as well. Later, suppose we form the pair 3 and 5, and 3 plus 5 will be equal to 8. So now we have to calculate dp of 2 and 4. And when we sum 3 and 5, we will get 8, which is in the index map stored at index 7. So we will get dp of 4 and 7 plus 1, which was 2 plus 1 equal to 3, and so on. And this is how we will continue to fill in the rest of the dp. And throughout the iteration, we will be tracking the maximum length, which will be equal to 5, and that will be our answer. Here is a quick code walkthrough of the solution we just talked about. We have Java code on left and Python on right. First, we will create a dp table of size n into n to store lengths of Fibonacci-like subsequences. Let's also create a hash map to map array elements to their indices, and also define the max length to keep track of maximum sequence length found so far. And after storing the elements in the map, we will start the iteration on the array. From behind, we will traverse on the array backward such that I goes from n-1 to 0 and j goes from n-1 to I, and we try to form the pair. First, we will get the values I and j from the array and set the current length to 2 based on these pairs. Now, we will calculate the third element, which is sum of first and second, and check if it is present in the index map. If it is, then we get its index from the index map and update the length of the current sequence starting with indices ij using the dp recurrence formula, and also update the maximum length from the current length. Once we are done with this pair, we store its length in the dp table and continue the iteration with the next pair. And in the end, if the maximum length of any Fibonacci-like sequence is at least 3, we will return the answer, otherwise we will return 0. Now in terms of time complexity, it will be O of n square, because we are running two nested loops to form the pairs and calculating the lengths of subsequences starting from those pairs. And in terms of space complexity, it will be O of n square, as storing the elements in the dp table take O of n square space, and storing the elements in the index map takes O of n space. Hence, overall space complexity will be O of n square. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.